Today we are going to discuss about the channel coding techniques that is mostly used in wireless communication in order to minimize the noise that has been added during the propagation of the signals. So in today's session we will discuss the basic application of the channel coding. So the first one is the Hamming codes. So Hamming code is quite important codes, and it is used in many applications like computing, telecommunications, data compressions, and even in block turbo codes. The structure of the Hamming code is you can write like this: k comma n, where k is the length of the message bits and n is the length of the code word bits. Usually on the transmitting side we are use encoder to encode the message bit, like we are going to add extra redundant bits or the parity bit to the message so that we can generate the code word. And similarly on the receiving side we need parity check matrix. So let's first discuss the transmitter side. There we are going to encode the message. Mapping from the set of k information sequence, like the k information sequence, to the corresponding code word of length n can be represented by generator matrix. Like mostly the generator matrix is used to encode the message, and the generator matrix can be written in different forms. Even you can generate the generator matrix using progressive edge growth algorithm, or there are many other methods that has been used in research in order to generate the generator matrix. But suppose for this particular and simple course we are going to give you an example of the generator matrix, like the generator matrix is given for you. So like if you see the structure of this generator matrix, so you can say that it consists of two parts. This first part you can easily say that this is the identity matrix. So this is the identity matrix. And this second part you can say this is the parity bits. So if you have a message in this format u1, u2, u3, u4, so it means that you have a 4-bit message, and then you want to convert that message, or you want to encode that message using this generator matrix. The code word will be equals to c multiplied equals to u multiplied by g, and then in that case you can generate the code word. For example, if you multiply that with this generator matrix, then you can see the simple multiplication matrix multiplication. Like you see, the first one is the identity matrix. So first u1 will be multiplied with this first column. So that is why there is a 1 only. So u1, and then for the second column u2 will be multiplied. Then again this will be multiplied with the second column. So there is 1 in place of u2. So that is why u2. The third column again multiplied with these 4 bits, and you can say the third bit is 1, so that is why you can see u3, and then the fourth column on the fourth place you can see 1, so that is why it is u4. But for the parity bits here you can see, if you multiply this first the fifth column, you can say this is for u1, this is u2, this is u3, and this is u4. So if u1 multiplied by u1, so the answer is 1. U2 multiplied by 1, answer is u2. u3 multiplied by 1, answer is u3, and u4 multiplied by 0, answer is 0. So that is why your fifth one is the parity bit. So this one you can see, this is u1 plus u2 plus u3. Similarly, this one is again u2 plus u3 plus u4. So you can see u2 plus u3 u4. And this one is u1 plus u2 plus u4. So u1 plus u2 plus u4. For example, rather than giving the journal bits, you can give the bits in this format: 1, 0, 0, and 1. And from here even you can say, okay, your message will appear in front of the code word. So you can see your message appear in the front of the code word, and the remaining is the parity bits. Like here u1 plus u2 plus u3. So u1 plus u2 plus u3. So 1 plus 0 plus 0, the answer is 1. So that is 1. So again here, so this one is 0, 0 and then 1. So 0 plus 1, answer is 1. So this one is 1 and then this is 0 and then this is 1. So 1 plus 0 plus 1, the answer is 0. So this is the code word that you are getting after multiplying from the generator matrix, and then you can write this code word in this format: 4, 7. Like 4 is the length of the message bit and 7 is the length of the code word bit. And second part is on the receiving side, like when the message is propagated, when the code word is propagated over the channel, then on the receiving side, when you receive the code word from the noisy channel, then you need to decode it. So for the decoding purpose, we need parity check matrix. So, but here, so it means that you need to generate the parity check matrix, you need to produce the parity check matrix. Again, there are many different algorithms in order to generate the parity check matrix, but for the sake of simplicity, we are just giving some little information here about the generation of the parity check matrix and the generation of the generator matrix. For example, if your generator matrix is given in this format, like here you can see identity matrix oblique parity matrix. So similarly here, the identity matrix oblique parity matrix, then you can generate straight away the H matrix using this formula: P transpose oblique I n minus k. In this case, n is 7, k is 4, so identity matrix will be I 3 by 3. So like here, from this we can easily generate the H matrix. Like here, first is the P transpose. So what is this? P. So we are going to taking the transpose of that one. So 1, 0 and then 1, you can see. So again then 1, 1 and then 1. So again 1, 1 and then 0. So again 0, 1 and then 1. And then this other one is the identity matrix, that is 3 by 3. So 1, 0, 0, 0, 1, 0, 0, 0 and then 1. So that is the generation of the parity check matrix if your generator matrix is given in this format. So you need to keep this thing in mind, that since a code word C is orthogonal to all rows of H, then we can conclude that if you multiply the code word with the transpose of H parity check matrix, then the answer should be 0. So if the answer is 0, then you can easily say that this is the exact code word. We are going to perform this method using an example when you are like on the encoding side, or you can say on the transmitter side, you need a code word. So code word is equals to generator matrix multiplied by the message bits. So suppose in this example, the generator matrix is given as well. So you can see this generator matrix is quite different from this generator matrix here, because this generator matrix, the pattern is IK oblique P, but this is totally different from here. But suppose this is given for you, this is the generator matrix and this is the message bits x1, x2, x3, x4, 4 message bit and the length of the generator matrix. So you can see how many rows: 1, 2, 3, 4, 5, 6 and then 7. So it means that you can have a 7 bit code word. Okay, Y is your code word and X is message bit. For example, so Y is code word, so it means that Y will be equals to Y1, Y2, Y3, Y4, Y5, Y6 and then Y7. So you can calculate each bit by using again the multiplication procedure. Like you can multiply this column with this row, like row column multiplication. So x1 multiplied by 1, or you can say 1 multiplied by x1, 1 multiplied by x1, and then XOR, so this is XOR basically, XOR 1 multiplied by x2, 1 multiplied by x2, and then again XOR 0 multiplied by x3, and then plus 1 multiplied by x4. So 1 multiplied by x1 is x1, 1 multiplied by x2, x2, 0 multiplied by x3 is 0. So 1 multiplied by x4 is x4. So y1 is equals to x1, so XOR x2, XOR x4. And then again y2, so again y2, so x1 multiplied by 1 plus 0 multiplied by x2 plus 1 multiplied by x3 plus 1 multiplied by x4. So the answer will be x1 XOR x3 XOR x4. So x1 XOR x3 x4. So here you can see this is x1 multiplied by all zeros, so the y3 will be equal to x1 and so on. So I am leaving this the further part for you, so you can multiply this and then you will end up with the exact answer, what are y3, y4, y6, y7. So from here you can easily say that your message bits, the position of your message bit in this particular code word, like here, so y3 is equals to x1. So similarly in all your code word here, it will be equals to x2, it will be equals to x3, it will be equals to x4. So these are the message bit in your code word. The other y1, y2, y4. So these are the parity bits. So these are the parity bits and these are the message bit in your code word. And you know on the designing of the encoding. For example, if you have these are the bits 1, 0, 1, 1. So this is the message bit. And using this formula, if you want to encode your message, you can straightforwardly write like y1 will be x1 plus x2 plus x4 here. y1 will be equals to x1 plus x2 plus x4. So that is why, so 1 plus 0 plus 1, the answer will be 0 and so on. And then you will end up with the y, so which is equals to y1, y2, so y3, y4, y5, so y6 and then y7 here. So you can say, so these are your message bits, this one and this one. So this is your x. So you can see 1 0 1 1. So 1 0 1 1. And then on the decoding side, so on the receiving side, when your message y is transmitted over noisy channel and received as y hat, because y hat is not the message, y hat is the message that you will receive after the propagation, after the noisy channel. So then you need to do the decoding. So decoding is done using parity check matrix at SH, where you can write a formula, or you can write this like check. So you can say that if S is equals to H multiplied by Y hat. So S basically your syndrome, so and then you can write H. So here again, as I said, in this particular case H is given as well, but there are, again I said, there are many other methods that you can generate H, but for this particular example we are giving you H. So this H is given always. So this is your message that you received from the channel. So S will be equals to H multiplied by Y transpose. So that is Y, so Y transpose. So what are the rules? Like how can we say that this is the exact code word, or if there's a bit that has been flipped, how can we correct it? So using the resultant n minus k, so n is 7, k is 4, so 7 minus 4 is equals to 3-bit syndrome. So this is 3-bit syndrome, 1, 2, 3. Hamming decoder decides if there are any bit error in Y hat. So these are the rules that you need to consider, that you need to take care of. If S is equals to all zeros, all 0 bit, then decoder think no error. So though it might be wrong as well. So if this is correct, like if you multiply H with the received code word and the answer is 0, then it outputs X hat, and we know X hat is your Y3, Y5, Y6 and then Y7. So that is why it outputs X hat. So that is Y3 hat, Y5 hat, Y6 hat and then Y7 hat, because we know that our message or our information bit is on these particular position, like our first bit is at position Y3, second bit at position Y5, third bit at position Y6 and fourth bit at position Y7 in our generator matrix. But second case, if suppose that S is not equals to 0, like if you multiply this H and this received code word and the answer is not equals to 0, then the 3-bit number, like this 3-bit number is converted into a decimal number. So no, we know that the 3-bit number that we know that if it is 3-bit number, so then the answer is equals to 7. So maximum is 7 and minimum is, so minimum is 1. So you can have a decimal number from 1 to 7, 1 2 3 4 5 6 and 7. So this is the decimal conversion, that how can you convert the 3-bit into a decimal number. And then we see that s is not equals to 0, then the decoder think that the ith bit, so ith bit means that the converter, that you have converted the number I, so I might be equals to 1. So if I is equals to 1, though it means that first bit, the decoder will think that the first bit in y hat has been flipped by a bit error. If I is equals to 3 or if I is equals to 5, then the decoder will think that the fifth bit in y hat has been flipped by a bit error. Again, it may be wrong though, because it depends on the capability of the decoder, that how many bits it can correct. So then the decoder flip the ith bit, so the ith bit from here, so which bit? So the decoder will flip the ith bit in y hat. Okay, so you need to be very careful that always flip the bit in y hat, not in y. So that is why, so you flip the bit in y hat before outputting x hat. So when you flip the bit in y hat, then you can output x hat, which is equals to y3, y5, y6 and then y7. So that's all for today's session. I hope that you understand this Hamming decode very well, and we have already given the examples, but still if you have any question, you can write your question in the comment box. We will try our best to answer the questions. Thank you for watching this video.